Hi everybody. We've been asked to put together a very quick video about how our technology works by a number of folks, so I'm just going to put this together, send it out to you guys, and try and walk you through how our technology functions right from the hardware through the software, what the scans look like, what positioning look like, and hopefully that will be able to give you guys a good sense of how things are working in the absence of a live demo. So the first thing I'm going to show you are these two units. These are our sort of engineering versions. The functionality and the electronics are all identical to our production versions, but for the purposes of use in our office space where we are right now, it's a lot easier for us to have these sort of engineering platforms that we can take apart and replace things much more easily than we can with these. So that's what you're going to see functioning today, but they are functionally identical to the ones that are being mass-produced in the next 6 weeks. So these guys are, we call them Johnny 5. Johnny 5, as I've probably told you already, is composed of a LiDAR sensor, a bunch of different radios, and a bunch of different sensors that help us do what we're doing right now. Johnny 5 can be mounted upside down on the ceiling, or as we have it in our office right now, mounted on the wall. And so what I'm going to do next is kick off a scan with Johnny 5 and show you how he starts to move. And we'll show you the results of that scan after a couple of minutes. Okay, so we're back again, about to kick off a scan. This is a part of our dashboard software, cloud-based, available through the web. And what you're seeing here is a list of the units that are currently online and mounted in our office space. Down the right here, you can see I can choose the density of scan we're going to create. For the purposes of this demo, we're going to create high-density scans. And then we have a couple of choices up here. We have, and I'm just going to press the button Scan Now. Yes. And you're going to see all of these guys eventually respond, and they start with the message calibrating. And what you can see here on the wall is a unit that has responded to the calibration request. And what it's doing is pretty much moving around to orient its compass, orient its gyroscopes, and all the various other sensors. And essentially the goal of that is to figure out how it's mounted in the space. Figure out where down is, figure out where up is, understand whether it's facing northwest, southeast, is it mounted on the wall. All of those things are really important information that we need in order to be able to compose the maps that it creates later on. Okay, so a couple minutes later, Johnny 5 has finished calibrating, and here you see he is just getting started with doing a map. So because he's mounted on the wall, he knows he's just going to only have to do 90-degree tilts this time. And you see he moves his eyes up and down and just scans the entire space slice by slice, back and forth. After each slice he rotates a little bit. This has been slowed down so that we can sort of talk through and give it a decent demo. But he is creating this map slice by slice, and he'll rotate after each one. Probably can't see him rotate because we've done a high density scan, which means the rotations are very, very fine in between each tilt. But this is basically what Johnny 5 looks like in essentially slow motion while he creates a scan of the space. Okay, it's a couple minutes later. The scans have completed on all of the units in the space. And what I'm going to do is just kind of pan around so you get a sense of what this space looks like. And then I'll show you the different 3D models that these guys have scanned and put together, and how we compose composite 3D models and then onto 2D floor plans. So if I just if I move the camera around a little bit, you can see where this particular sensor was mounted, and then I can kind of pan around the space. You can see what kind of open space. This is a shared office space that we're in right now with a bunch of other companies, but there are rows of these open concept desks. There's a bunch of these pillars, and that's sort of what it looks like from the perspective of the scanner that I'm about to show you next. And I'll show you the 3D scan right now. So this is our this is back in our console. This was 402. I can hit play to rebuild the scan as it saw it. And so this is our 3D viewer, and what you again see is now a point cloud representation of that space. Right? We can move it around and sort of view it from different angles. But you see the table that I'm currently working on. We see some of the details like the chairs and the pillars, the floor. Obviously, we see the walls off in the distance. Similarly, the scanner that's on the other side of this room put together this perspective. So this is the opposing perspective of the same room. And so this scanner is the scanner that we've been talking about so far has sort of been mounted somewhere over here in this perspective. And this is the opposite perspective of the same set of tables and chairs in the room. And we'll use these to compose a complete 3D model of the space. Okay, so what we're looking at here is our stitched 3D composite map of the two different perspectives that we were showing earlier. Obviously we can stitch in more, but it actually gets harder and harder to see as more different colors are overlaid. We use different colors so that we can kind of debug the scan. And so for purposes of clarity, we're just going to show two here. But what you're seeing is that the areas that are green are from one mapper. The areas that are red are from another, and because they're from opposing perspectives, they've kind of filled in all of the detail in the 3D map that each other has missed. And so this is the approach we take to being able to create this completely detailed 3D composite map of the spaces that we're deployed in. We take this. We obviously use it for a lot of things. We can extract details about the chairs and the tables and whatnot, but what we're going to show next is how we kind of take a slice through this 3D map and create a floor plan of this space. Okay, so we are back in the console now, and what you're looking at is a 2D floor plan that we've extracted from that 3D model. Obviously there's some detail in here that wasn't represented in the 3D model that I showed you. That's because there are extra mappers around the space that also pick up that detail, compose it into the 3D model that I was showing you, and we're able to pick up all that detail as well. For simplicity's sake, we were trying to show a much more understandable composite model than we would be able to if we included all of the 3D maps or mappers. So this is the IBM space that we are in. For reference, this is the location of the Johnny 5 unit that we first started talking about in this video, and the other one that we composed the model with is positioned over here, but there are ones around the rest of the space in order to pick up all this detail. So that's how we get the floor plan, and the floor plan is basically what we do is we analyze the 3D point cloud, we turn that into surfaces and planes, and straighten them out for purposes of making a nice looking floor plan. But we basically take a slice, a 2D slice at the height of the mappers in order to extract what we call this floor plan. So obviously a 2D slice through a 3D model turns into lines, and that's what you're seeing here. So the first thing, so that's the mapping portion of our system. Now, because all of the mappers know exactly where they are against this map, because they created it, they're able to monitor the space for Wi-Fi sources and do what we call trilateration. So if I turn that on, you can see all of the clients that it's picking up in the space. They'll kind of here. So it's picking up a number of Wi-Fi clients in the space. Occasionally you'll see these things sort of fly around as one of the units in the space may lose a signal, and we'll calculate the position as slightly different. But right now, because the space is kind of empty, it's actually mostly the computers and routers and whatnot that's in the space. So on a busier day, there's many more signals, but it's fairly quiet in here right now. Now, looking at individual dots for Wi-Fi trilateration is actually not that interesting, because Wi-Fi trilateration has pretty strong limits in terms of its how accurate it can be. But what it's great at is looking at aggregate data. So if I go and turn the heat map on, this is what most people are more interested in. If I turn the heat map on, what you start to see is the heat mapping data associated with the last 5 minutes. So we've set this to 5 minutes of decay, and you'll see right now it's a fairly light usage here, because as I said, it's fairly empty right now. But over time you can see it's aggregating in the center one, because that's where most of the signals that we have right now are being picked up. It's also where Jason and I are spending most of our time at the moment as we wander around doing this video. What you can see are a couple sources out here. These ones sort of represent Wi-Fi access points that are in the space. And you can see that right now there's nothing in this meeting room at the back here, or any of these meeting rooms, because as I said, it's Saturday and there's nobody here. We're also picking up a few signals that are outside. This is a fairly busy street outside right now, and it's a fairly nice day, so there are people outside. Okay. The last thing I want to show you is the Wi-Fi trilateration. We can trilaterate Wi-Fi and get that kind of positioning and that heat mapping data. We can do the same thing for Bluetooth, so we can pick up Bluetooth sources as well as BLE beacons. All of those have a limitation in terms of their accuracy, and they're best used for analytics and for aggregate data. But we are able to pick up. We also have ultra-wideband integrated into our system, which allows us to do very, very precise positioning of people. Let me turn the heat map off so it's less distracting and clearer. So what you're seeing here is 2 dots that are, so this red dot that's moving around right now is a tag. And as I move down, as I walk away from the camera, you'll see it move, and it's tracking my position with accuracy to about 15 centimeters. Hopefully you can still hear me as I come back. It should return to where we started, which is great. And so we use this kind of positioning for our asset tracking use cases. So for customers that need very, very precise positioning of assets and even employee tracking, these battery-powered tags can provide that level of precision. Okay, so that's a pretty whirlwind tour of the end-to-end of our technology, how it works. So we went through kicking off a scan, the calibration of the self-calibration of the units in terms of their positioning, as well as in terms of their own positioning, as well as how they sense Wi-Fi and other signals in this space. We showed how the mapping actually functions from the sensor's perspective. We showed what the 3D models look like, what they look like when we start to compose them, how we extract 2D floor plans out of that 3D model, and then how we can use the fact that these sensors know where they are in this space to automatically start trilaterating and positioning things. So we showed Wi-Fi trilateration, not only being able to pick up and start counting the individual sources of Wi-Fi that are in the space, but also create heat maps and aggregate data about where are different signals spending time in the space. So the use case there is really about foot traffic analytics. Signals that come off your phone are a Wi-Fi source that can be picked up and tracked and collect aggregate data about it. The last thing we showed was precise tracking of ultra-wideband tags, which look a little bit like this. These are, again, just engineering versions. But these things can be battery-powered, slapped onto an asset, or included in an employee's badge, and you can get very accurate centimeter-level precision of positioning with these things. The key point is that other than installing these Johnny 5 units on the wall, giving them power, the rest of it was automatic, essentially. The scanning of the space, the creation of the map, and the positioning of the signals in the space, all of that involved no further interaction from me. So that's it. That's the basic technology that supports this instant GPS platform that we've built. And if you have any further questions, obviously reach out to me over email. Thank you very much.